Amid the arid Rocky Mountains along the Mediterranean coast, a vast construction site is gradually rewriting Turkey's energy future. This is the Akkuyu Nuclear Power Plant, a mega project worth more than 25 billion United States dollars and one of the boldest moves in the country's energy history. The project consists of 4 massive nuclear power units with a total capacity of 4.8 gigawatts, enough to meet approximately 10% of Turkey's electricity demand. The entire project is being financed and constructed by Russia through the Rosatom Corporation, creating an energy partnership lasting for decades between a NATO member and Moscow. So how can a massive nuclear machine be built, controlled, and operated on a rocky coastline, then transformed into a source of electricity for millions of people? In this video, join Mandarin Tech as we explore the construction of the Akkuyu mega project. For many years, Türkiye has had to obtain most of its energy from other countries. But with its level of dependence reaching approximately 72%, every crisis or price fluctuation can place direct pressure on the economy. In 2028, when construction of Akkuyu officially began on the Mediterranean coast, it opened a journey toward a more stable and self-reliant energy future. More than simply an energy project, Akkuyu is also regarded as a test of Türkiye's nuclear industrial ambitions. Once fully operational, the plant will help anchor a gradually developed technical capabilities, train a specialized workforce, and create opportunities to develop additional nuclear projects in the future. The greatest difference lies in the build-own-operate model, under which Russia is responsible for everything from design, construction, and maintenance to operation and eventual decommissioning at the end of the project's life cycle. This has raised concerns within NATO. When a strategic member becomes deeply dependent on Moscow's technology, fuel, and nuclear supply chain, Akkuyu is no longer merely a power plant, but a point where energy needs, economic interests, and geopolitical competition intersect for decades. To build Türkiye's first nuclear power plant, engineers had to gradually transform this isolated area into a fully developed industrial site. Bulldozers began removing the topsoil in thin layers, completely clearing away organic soil and unstable loose material. Excavation and rock drilling equipment was then brought in to deal with large rock masses. Hydraulic breakers and controlled blasting were used to break up the rock structure without generating vibrations beyond the permitted limits in the surrounding area. The excavated material was sorted. Reusable material was transferred to backfilling areas, while unsuitable material was transported out of the construction site. The terrain was then graded according to each designed elevation, creating stable construction terraces. The fill layers were leveled and compacted using specialized equipment to achieve the required density, ensuring that the roads and working platforms could withstand long-term loads. Alongside the site grading work, temporary construction roads were opened along the mountainside. Their foundations were reinforced with multiple layers of material, from crushed stone to graded aggregate, to distribute the loads from concrete trucks. In areas with weak ground conditions, engineers also installed geogrids or reinforcement piles to increase load-bearing capacity. To create a stable foundation for the entire plant, the reactor building foundation pit is excavated layer by layer. Excavators remove the upper soil and rock, while drilling and breaking equipment is used to process the harder rock formations. Once the design elevation is reached, loose rock, weathered sections, and any remaining weak points are removed. Large cracks are cleaned and then filled with grout to create a stable, continuous rock foundation. On this surface, a layer of blinding concrete is poured to create a clean and level working base. The waterproofing and drainage systems, together with instruments for monitoring moisture and foundation movement, are installed above it. Next, thousands of steel bars are woven into multiple dense layers of reinforcement, incorporating technical pipelines, embedded steel plates, starter bars, and anchoring components for the structures above. Concrete is supplied continuously from on-site batching plants and distributed by several concrete pumps operating simultaneously, helping to limit construction joints and prevent weak interfaces from forming within the structure. Once the foundation slab reaches the required strength, the structure begins to rise. That massive concrete foundation became the load-bearing base for the entire reactor building throughout decades of operation. On the newly completed foundation slab, the central section of the reactor building begins to take shape. The first device moved into position is the core catcher, which is designed to contain molten material if the reactor core suffers a serious accident. The core catcher is lifted by a heavy-duty crane and lowered precisely into position beneath the center of the reactor vessel. This operation must be carried out early, because once the upper levels and the dome have been completed, the device can no longer be brought inside. After the core catcher is secured, the construction team begins erecting the surrounding reinforced concrete walls. The reinforcement bars are connected to the starter bars extending from the foundation slab, while the formwork is installed in separate sections and must be positioned correctly before each concrete pour. The reactor building structure continues to rise level by level. Reinforcement frames and steel liners are assembled into enormous circular sections at ground level, then lifted by crane and stacked to form the inner protective shell. Finally, the polar crane is installed inside the reactor building to support equipment installation and refueling. However, the upper section of the reactor building remains open. This opening provides the access route for bringing the reactor pressure vessel and other heavy equipment inside during the next stage. While the reactor building structure is being erected at Akkuyu, the reactor is manufactured at a specialized mechanical engineering facility. The manufacturing process begins with enormous steel billets, which are heated and then forged under immense pressure to create a uniform metal structure. The billets are subsequently machined into thick-walled vessel rings, inspected using ultrasonic testing, and joined together by welds. Once the reactor vessel meets the required standards, it is transported by a specialized vehicle to the port, loaded onto a cargo ship, and delivered to Akkuyu. At the construction site port, a quay crane transfers the equipment onto a multi-axle transport vehicle, which carries it to the reactor building along a specially prepared load-bearing route. The reactor vessel is transported in a horizontal position. At the installation site, the main crane works together with auxiliary equipment to slowly rotate the steel vessel into a vertical position. The vessel is then lifted through the open roof and slowly lowered onto the support ring located at the center of the building. The surveying team continuously checks the centerline, elevation, and vertical alignment before the vessel is secured. After this milestone, the steam generators, circulation pumps, and main pipelines are installed around it. Once the major equipment is in position, the steel frame of the dome is assembled at ground level, attached to the cable system, and lifted to the top of the structure. The dome is slowly lowered, aligned with the walls below, then secured, welded, and concreted to completely enclose the reactor building. When fuel is loaded into the reactor vessel of the Akkuyu Nuclear Power Plant, nuclear fission begins generating heat. Inside the Viver 1200 reactor core are hundreds of fuel assemblies containing uranium dioxide pellets. When uranium nuclei absorb neutrons, they split apart, releasing heat and producing additional neutrons, thereby creating a chain reaction. Water flows through the core to absorb heat while also slowing down the neutrons, helping the reaction remain stable. The control rods are raised or lowered to change the number of available neutrons and regulate the reactor's power output. The entire process is closely monitored by sensors to detect and respond to any changes. From the reactor core, the heated water carries thermal energy to the steam generators, where it heats a separate water circuit and turns it into high-pressure steam. The steam rushes through the turbine blades, causing the turbine shaft to rotate continuously. This shaft is connected to a generator, which converts the mechanical motion into electricity. The voltage is then increased to the required level, and the electricity is transmitted through power lines into Türkiye's national grid. After losing its heat, the steam is cooled and condensed back into water, then pumped to the steam generators to begin a new cycle. As of July 2026, all 4 power units at Akkuyu remain classified as under construction. Unit 1 has entered the commissioning stage, with several major systems being tested using dummy fuel assemblies. Meanwhile, the other 3 units are still undergoing equipment installation, structural completion, and construction of auxiliary facilities. The greatest challenge is proving that the entire plant can operate safely and reliably for decades. Once it passes this verification stage, Akkuyu will represent far more than an ordinary power plant. The project could help Türkiye reduce pressure from energy imports, provide a stable source of baseload electricity for the economy, and gradually develop a domestic nuclear engineering workforce. Its construction is also supporting the growth of mechanical engineering, materials, logistics, and technical training. However, these benefits come with long-term dependence on Russian technology, fuel, and operational services, making Akkuyu both a symbol of Türkiye's energy ambitions and a strategic commitment that will last for decades. While Türkiye's Akkuyu harnesses the power hidden within the atom, Tajikistan is placing its energy future in the Rogun Dam, where water plunges from the mountains of Central Asia. Tajikistan is one of the poorest countries in Central Asia, landlocked, with limited fossil fuel resources, a population of just over 10 million people. Yet in a remote valley along the Vaksh River, this small nation is pursuing an ambition far beyond its own scale, building the tallest dam in human history. With an estimated total cost of around $8 billion, the Rogun Dam is designed to stand 335 meters tall, surpassing every existing dam in any skyscraper currently standing in the world. The project is planned to generate 3,600 megawatts of electricity, equivalent to the combined capacity of multiple nuclear power units. The idea of the Rogun Dam is not a product of the 21st century. It first emerged in the 1960s, when Tajikistan was still a republic of the Soviet Union. In the context of the Cold War, Moscow was pursuing an ambitious strategy, industrializing its peripheral regions, especially Central Asia, through massive infrastructure projects. The Vaksh River, a major tributary of the Amu Darya system, quickly came into focus. With its powerful flow, high mountain terrain, and dramatic elevation drop, this was one of the few locations in the world capable of supporting the construction of ultra-high dams. In 1976, the Soviet Union officially launched the Rogun project. The objective was clear: to build a dam that would surpass all previous hydropower projects, one capable of controlling the river, generating electricity on a massive scale, and regulating water for the entire region. But history did not follow the plan. After the collapse of the Soviet Union in 1991, Tajikistan descended into civil war. Its economy collapsed, and Rogun, still only a partially built construction site, was abandoned. It would take more than 2 decades for Rogun to have a chance at revival. According to engineers, when completed, the Rogun Dam will stand 1,099 feet tall, equivalent to approximately 340 meters. This will make it the tallest dam ever built. The Rogun hydropower plant is designed with 6 turbine units, with a total installed capacity of 3,600 megawatts. This amount is sufficient to double Tajikistan's current electricity output, creating a significant surplus of power during the summer months. Rogun is not a conventional concrete dam. It is a rock-filled dam with a central clay core. The dam body is formed from hundreds of millions of tons of rock and gravel, compacted layer by layer. The clay core serves as an impermeable barrier, while the massive rock-filled shoulders provide structural stability and energy absorption. The reservoir behind the dam has a capacity of approximately 13 cubic kilometers of water, making Rogun one of the largest reservoirs in the region. This volume allows for seasonal flow, regulation, more stable power generation, and support for irrigation in downstream areas. The first 2 turbine units began generating electricity in 2018 and 2019, marking the transition from a purely construction site to an operating power plant. The electricity produced during this phase both supplies domestic demand and allows engineers to verify the design and operating systems under real conditions. According to the current plan, the dam body is expected to reach its design height around the year 2029. However, reservoir impoundment will be carried out cautiously and over a longer period. It is projected that the Rogun Reservoir will reach its maximum water level around the year 2036, fully completing the dam's role in regulation and power generation. That is the story of Tajikistan's energy ambitions. Meanwhile, in Türkiye, Akkuyu is still gradually transforming a vast nuclear construction site into a source of electricity for the entire country. From a rocky coastline to a massive nuclear complex, Akkuyu demonstrates how ambition can create extraordinary structures. Behind its concrete domes, thousands of engineers are still installing, inspecting, and testing each system. At the same time, Russia's long-term role in ownership, fuel supply, and operational support means that Akkuyu is not merely an energy project, but also a complex strategic commitment. Do you think Akkuyu will help Türkiye achieve energy independence or create a new form of dependence? Share your opinion in the comments, and remember to like and subscribe to Mandarin Tech to continue exploring the technologies and mega projects that are changing the world.